to discuss today. We have it. Everyone. We'll have like half of the first lecture that we had last week, and then this lecture is like I think how it's like 20 slides, something like that. Today I'm going to finish data link layer, so I'm not going to go to the network layer, because network layer has so many practical things with routing, with IP addressing, APR. These are things, subnets, that's very important. I want you to be more aware of those things. I need you to practice it a lot. So we do some things during the lecture and at the tutorials. So leave that until the next lecture. What are we doing today? We're doing the LANs in general, doing the bus evolution towards the switch, hubs. I'm going to show you how, let's say I plug and play me, what does that mean? How does it operate within switch? How do you do that self-learning within the tables? We do that as well. And that's it. Let's start with the LANs first. So the LAN in general are residing, again, when we said LANs, are residing in the second layer. With the second layer, that's your data link. The data link itself is divided into virtually into two sublayers. First sublayer is called the control, logical link control layer. And that's the part you don't need to be aware of, and there's nothing major happening there. Meanwhile, the other parts, which is the actual MAC layer, that's the part where you have the media access control layer. That's the part where we just describe the control protocols. Your actual channel partitioning, your random access, your taking turns. Everything's happening there. Your actual physical part of the address is stored in that part as well. But your physical address is stored in that second part of the actual sublayer of the actual LAN network. Physical layer, we differ according to the media, so I'm not worried about that at the moment. Let's move on. Ethernet. Ethernet is the most dominant technology within data link layers. The question is, why is it that dominant? It's been around since 1980s. People might say things evolved from Ethernet towards a better technology. So the question is, why Ethernet is still that dominant technology? We'll just introduce Ethernet at the moment. Ethernet is a traditional local area network LAN technology. So what's the Ethernet? Do you know what's the Ethernet? Have you ever seen the Ethernet? That's the Ethernet cable. It's the same. The protocol left behind the Ethernet is what we are going to introduce today. The structure of that frame is you've been seeing that Ethernet RJ where you see the actual connection. That's the Ethernet. That's your data link connection. So that's the main part we are going to discuss today. It's fast becoming a wide area network technology also. When Ethernet started, which was just basically introduced to the local area network, it never was thought to be a wide area network. Why do you think that was? So how does that evolve? What changed? How do you get a wide area? Yeah, again, internet was introduced there, but how does it become a wide area network? What happened? What's the main thing you want within a wide area network? Connection and data. Data by data, what do you mean? What's the main thing within internet you want? What do you want? When you buy internet, what do you want? Yes, so what do you buy? Speed. You want a speed, you want a bandwidth, you want a fast speed bandwidth that occupy all the information within a limit. So people might say I want to buy 100 megabit per second, which I don't want, but I want it there. It's a speed. I like to have an operating system that operates very fast without any lagging. Again, speed is very high demand. Download is the second thing, but speed is a major thing. So to create a wide area network, you need to cover that speed. So regardless of the LAN itself, were introduced at the beginning, it started with a very simple 1 megabit per second, but that evolved until now. We have 1 giga, sometimes 10 giga with LAN technologies. So that evolved heavily. So LAN, people behind the Ethernet, when I say Ethernet, there are people who are trying to develop it, standardize everything. So they are trying to catch up with everything new. So they never left the Ethernet as it was the beginning, 1 mega, 10 mega. They evolved towards the 10 giga. Even there's a 100 giga at the moment. I'm not aware of that, but it's available. So the thing they are trying to catch is the speed. That's the main thing you want to know. So the main task of all LANs is to take care of all the local delivery of the frames. So from the beginning, we said switches, Ethernets, LANs, routers, main part is to forward those data, those frames, those bits from the source, so it's a destination. So the main duty of the LAN is to take care of the local delivery of frames. I'm using the word frames, why? Why packets, frames? Why I'm using frames? Why not datagrams? because of the data link technology. What do you use within the frame, within the data link? We use a frame. Remember the encapsulation? You have frames. That's why I'm using the word frames. You've seen a bit why, for example, hubs use bits, because they are physical devices rather than the actual switch devices with which you work on a data link. Okay, so take a frame from an interface. When I say an interface, now I'm dealing with either the interface of your actual switch or the interface of the actual machine. What is your interface within the machine or the actual hub or the switch? What is it when I say interface? What do I mean? The operating system interface, having an actual graphical user interface, for example, as an interface. But with physical devices, what do you mean by interface? Yeah? Exactly where you join. So it's exactly where the Ethernet plug, the RJ plugs into the actual port. That's the interface. The same thing, vice versa, with the machine, the PC. How you have the NIC, the card, the network interface card, and then the Ethernet will plug into it. So that's your interface, in other words. What essential information is needed to deliver frame? Now tell me, what is the essential information to deliver frame?
Frame header.
Sorry?
Header. Frame header.
What's that?
The header of the frame.
What does it have? What does it hold?
Address.
Address? Exactly,
yeah.
that's what you need. You want the address. So to deliver any data from any source to any destination, you need to have the address. What's the address within your data link? It will be your MAC addresses. Your physical address are your MAC addresses. So we are dealing today with the MAC address and the physical address of the actual LANs. Traditional Ethernet. It started dominant wired LAN technology, standardized by IEEE in 1985. That's the first sketch of the actual Ethernet. It started in the beginning with a controller. You know that's two parts of the actual Ethernet. Controller, and then you have the interface, which is now, that's your MAC part, the MAC addressing, the other parts of it. And then you have the interface of the cable connected to the Ethernet, to the actual net. That's how it started. It was cheap for $20 to buy an actual network interface card. The major part of that dominance, it was very cheap. So what's $20 in compared to that old technology where you have an Ethernet connection up to 10 gig? At the beginning it was up to 10 meg. So that was very cheap compared to other technologies. So one of the main things within Ethernet, it was very cheap compared to ATM with ring connection. So that was the first part where everyone was going. Every administrator, software technology was going for the Ethernet. And when Ethernet started to get dominant and everyone was using it, I just mentioned to one of the groups, even if other technology came in and tried to break a lower price, how much will it cost you to change the infrastructure of your company? Millions. So even if you had a better technology in the future, which is, when I say better, is not dominantly better, it's just a higher bit speed, less, for example, more reliability, whatever that is. But Ethernet is very cheap, and to actually change the whole infrastructure with not doing a lot of things, it's not worth it. So that was the first part where actually Ethernet started to be used by every company at the moment. It's very, first of all, we use the LAN technology. I'll just explain that. It's simple, cheaper than token-based LANs and ATM. When they started, it was very cheap. They started to get dominant, so it was very cheap. They introduced it with a very cheap price. And until now, it's very cheap to buy a NIC card. How much does it cost? I don't know. Maybe now it's what you call it, a built-in in the motherboard. But if it's not, you buy it for a few quid. I'm not sure how much. But it's very cheap. So it's still cheap. They kept up to speed, that's major thing. Kept up to speed, went up towards 100 gigabit per second, and even maybe higher at the moment. So they are trying to keep that dominant within the field. They don't want to be left apart from the other technologies like ATM and frame relay. They're trying to keep always the speed within the Ethernet as well. So even though the technology came in and was higher with the speed, but Ethernet is still being used widely at the moment. I doubt there's any place that you do not use Ethernet. Either in my office now I use Ethernet. Evolution of star topology. When we were trying to describe last lecture, our dose medium access control, I needed to explain the first part that having this bus technology, the series of bus, the major issue with it is your actual collision. There's no actual device that controls that packets going in and out. The only place it's being controlled is by those protocols I defined, the three categories, like the other parts. So the amount of collision happening is huge. The amount of speed, so when you have a collision, what happens? What's the consequences? A collision, what happens?
Drops the packet.
drop the packets. What that consequence as well will create what? If your speed of that, what will happen to the actual bandwidth? Wastage of the actual bandwidth. When I say wastage, what does that mean? Speed drops. So if you have 10 megabit per second, with this bus series, that goes down to maybe 4 megabit per second because of that collision. So don't take collision as something simple. You just say collide and then retransmit. You create overhead, you create delay, and you create wastage to the actual bandwidth. That reduces speed. And again, having better technology should be available to rectify that issue. So with the bus topology, was popular in the mid-90s, but eventually was going towards a dying stage because it was suffering heavily with the collision, which led towards a less speed of the actual bandwidth. All nodes in the same collision domain, transmission from different nodes can collide with each other, which we just explained a moment. That was the major issue with the bus series, collision. So how was it in the beginning? The traditional Ethernet started with a 10 megabit per second Ethernet. It has so many options. I'm not going to bother you with full details of Ethernet because it's not like 10 slides of actual each option of your Ethernets. The speed, the type of the signal, the actual part of the where you are using the switch or hub. That's very boring. In a sense, I want you just to understand the main traditional part with the actual Ethernets. They have 5 different options. The topology that they did was 4 based on the bus, 1 was based on a hub. And it's star technology. At distance, we cannot cover more than 2.5 kilometers. That's it. But when I say 2.5, I'm using repeaters. Not basically, I'm using a full cable of 2.5 kilo. And I explain repeaters in the next slide. What is it and how does it work? Each segment is 500 meters connected by 4 repeaters. So again, I'm just describing that part in this slide. This is what's called 10 base 5, the most popular of the 5 options. Just have a look at this. That's your first part, the 10 base 5 Ethernet. Just look at the topology. Each segment is connected by a repeater. Does anyone know what does a repeater do? What's the actual job of the repeater? Yeah?
Forward.
Sorry? Oh, yeah. So it's actually taking the lowest part of the signal and trying to amplify the actual signal towards a higher. What will that consequence? So if I'm sending 5 segments, the first one has a repeater 1, the signal is going in 1 megabit per second, reach that final stage, and then being repeated towards another segment. What will that consequence? What will that affect? Because I'm saying it only has 500 to 2.5 kilometer. Why do I stop there? Why don't I just use that repeater? What's happening? In each segment I repeat the signal. What happened to the actual, to the original signal? What do you think? Exactly. So for the signal, when you repeat that signal, you're not taking the full speed of the signal. You're just taking less of that. So let's say you are taking 1 megabit per second. You repeat it. You're repeating 0.8 now, megabits. And then you repeat it 0.6, 0.5, 0.4, 3, 2, until that becomes unusable. So therefore, there is an actual limit of 2.5 kilo to be used. That's mainly what's happening. Those repeaters cannot do the job for you yet. You'll be in effect of fading of the actual signal. That's the main part. It used to have a thick coax cable. You know the coax cables? The first antenna that we had within, for example, the UK, you have a shielded cable with the main. Have you seen a coax cable? I have a bit of cables around. I'll bring it the next time. It's like calculated, which is like a fiber optic. So you can see the fiber and actually inside the line, the actual twisted pair coax. I'll bring it next time to see the mediums that we have. Just have a look. They started with coax. That's the beginning. And that was very, very 2 signals going in and out. And I'll explain that. I think that's the next. Yeah, we have a shield actual connection of a cable. You don't need to be worried about those information. Again, now this is for you, just the sake of understanding what's happening in the evolution of actual topologies and networking. The problem of cabling was connectors from nodes to cable was very not convenient to use or hard for administration to do it. Therefore, they moved it to the twisted pair of cables and then to the RJs to be used. Increasing popularity of it. It was cheap to be used, but it was suffering from that side of not easy to implement. Sometimes it's very easy to have a twisted pair which stops everything. It's very easy to break it. If you have that break in the middle, the signal disappears. So it's not easy to have it played with around in a sense. So the evolution, why do we now have that evolution? Why I'm moving towards from a series bus towards a star topology? I'm moving to that topology just because I wanted to reduce collisions. That's basically what's happening. Trying to reduce collision in that topology, in that network. So they move from a star topology, so from a series bus towards a star topology. When I say star topology, I mean they are connected in a shape of star. There is number of users connected to as a device, a black box, whatever that black box is, hub, switch, router, connected to other devices. So this is how a star topology will look like, the star shape. They first started with something called hub. A hub was exactly your series bus inside the box. That cable connection that we had, you just seen it in a moment, was inside there. So, still having that collision issue. We're still having that problem of not having an advanced device that can create intelligence of a plug and play, can define, you need an administrator to control it, you need to configure the device, and you're still having that collision. So what have you done? What's the new with it? The only thing that has been created, you are reducing cables to be used between devices. Now the hub is reducing the number of cables, because hub will provide you that more efficiency than a repeater, put it that way. Because you have less cables being connected and more bigger LAN to create. So the hub was a bus in a box. Very rarely used. It was very fast. The switch created afterwards in 2000 came the switches. They are physical star topology, but logical bus topology, which has little more than a repeater, but it was dumb devices. I'll have it in full details. When I say dumb devices, you cannot plug and play. You need a configuration, an actual admin to configure your PC, your Mac within the hub. So when I say configure, you need to have associate your MAC address with the IP, with the port number inside the hub. So it's for you guys, you might say auto assign at the moment within the operating system, but in the past that wasn't that easy. Especially with big LANs, big networks. Switch was an intelligent devices. When they first started the switch, they started the plug and play. They had those multiple access control within the switch itself. Hubs doesn't provide those medium access control, so the collision is happening. Leave it to the end devices. Meanwhile, the switch actually activate that part, which enables a medium access control, controlling the sending and information of that actual packets. So in other words, inside the switch, there should never happen any collision. Collision should never happen. There are multiple simultaneously transmission inside those switches, so you can send and receive at the same time, because there is no collision. Nodes can transmit and receive simultaneously the same. Thus, they are full duplex technologies. I'm going to describe switch in full details later on, but at the moment, is that clear as a basis? What's happening? How are they evolving from one technology towards another? How do they need it, the star topology rather than the bus because of the collision and everything else? Any questions? Okay. Let's look at Ethernet structure. That's your Ethernet frame structure. We had the frame structure of point-to-point protocol when we had the flags. You remember you asking me why you have flags from the beginning and the end of that structure. In here, you see there is no flags. There's something called preamble, which is doing the same thing, but without in the end, just in the beginning. With that, then you'll raise a question. Why then that happens at the beginning, not happening in the end? I'll explain. Now, we said we are dealing with high speed. Point-to-point wasn't dealing with high speed. They needed to have a basic bit parts to actually define your structure. Enable the end devices to understand the beginning of the end of the actual protocols. Meanwhile, Ethernet are dealing with 100 gig. So how fast is that? What do we need? Do we need the flags? Or do you need something more advanced? They created something called preamble, where is defining 8 bytes, not 8 bits, 8 bytes. 7 of those just synchronizing and clocking the sending device and the receiving device. So you are clocking the time exactly and telling the device what I'm sending, how much is the speed, and how much packets I'm going to send. So in other words, you're telling the device everything in those 8 bytes. And sometimes you need even some sort of priority. You give it the final end byte, have some 2 bits in the end, which provides priority as well. So now the technology is becoming more advanced. So now returning to your question, why do I not have it in the end? Those 7 bytes are defining the beginning and the end of the actual packet structure. The frame, I should say, the frame itself. Yes?
So you say they're at the start of the that information, it tells where it is as well.
Exactly. So it tells the full information of that structure of the packet. You know why? Because the main thing of it is the synchronization between the sending and the receiving. That's the main part. You are clocking the time of the sending and the receiving. Everything is a clock time in networking. If the clock is not ideally synchronized, you send information, but this device is not anticipating to receive it in that speed. So you end up having that delay. If you don't clock it perfectly between the sending and receiving, you'll end up with a delay, which is a physical issue rather than an actual protocol. So now you need to clock those times between the two end devices at the major part at the beginning. That's a part of it, of the first part of the actual structure. Second part, address. What's the address now? It's very clear. Rather than having in a point-to-point an address where it's a fixed address, because you have one sender and one receiver, inside an actual data link within the actual receiver side, in here now we have a source address and a destination address, which is now becoming more interesting. When you say source address and a destination, what kind of address I'm using here? Which one is it? Anyone? Yeah, that's the one. Say card. The MAC address. I'm dealing now with a MAC address, with a source and a destination. I'm using a data link layer. I just have a MAC address. I'm dealing with a switch. So does that mean let's make now a conclusion. How does a switch look like as an architecture? How many layers do I have in a switch? 7. Wow. Don't give me numbers. Tell me why. 3, 2, 1, 6, 5, 8. They are 7 at the end, by the way. Tell me, how many do you have and why?
There's 5, but they usually 7.
No. Again, switch. First of all, no, not 3. The routers had 3. And why? Because they needed 3 as they are what? A network devices, where we have a network layer, data link, and a physical. What are switches? I just define them as data link devices. So how many layers do I have? 2 layers, exactly. I'll have a physical. You should have physical because your connection should be somewhere. If I just have a data link, it will never work. That means I have bits flying around without anywhere. So I need the physical part to actually pass the medium of the actual information. And the data link is actually doing the switch operation. So switch only have 2 layers. Compared to the router, we had 3 layers, if you remember. Compared to the actual architecture of a PC, we had 5. And 7 in the old part. No. It's not complicated. It's just a matter of understanding how does it work. So if I say it just operates within a physical address, that means just have a data link with a physical, of course. Physical is always there. It's like a bed and you carry it everywhere with you. Because you have a physical connection. But the data link is actually doing that part of cleverness, if you want to call it, the protocols. So addresses are 6 bytes, which has the source and the destination of those MAC addresses. And I'll explain what are MAC addresses, how many bits they are, and what type of decimal information there is. There is something called a type, which indicates high layer protocols, i.e. the protocol which is passing the packet to the MAC layer. So in other words, I'm taking what as an information here? What's inside the data? Your message. People say message, information. Yes, but what kind of? What are these? Where are they coming from? Return to the encapsulation thing. Yes, data. Well, what kind of data? What is it? Yeah, try it. Encapsulation, what do we have? Encapsulation, just remember. We had 5 layers. Let me just put space in. We had 5 layers. Sending information. What did we have exactly? Message passing on from higher layers to lower layers. Is that right?
Yeah.
Physical as a message passed on towards your transport, where you had been creating a segment. When you pass segment towards this layer, the network, what are you creating? A datagram. So a datagram is passed on to where? To your data link layer. So exactly inside your data, you have a datagram. Okay? That's the kind of data you have. So now when I say a type, you're defining exactly what kind of datagram that's being sent to it from the higher layer. Is it Is it an IP address or is it something HDLC, for example? Might be an IP address. So you need to define that type to as a destination. That's the place inside the type you define that. What kind of protocol is sending this data from? What is the CRC?
Redundant.
That's the what does it do? Check for errors.
Check.
The question is, if I check for errors only, is this a reliable service or no? Yes or no? Why? No. What do you need with an actual reliable service? You don't need a correction. What do you need mainly? You remember the word. You need acknowledgement or a negative acknowledgement within your actual sliding window. If you have that acknowledgement, then you're creating that reliability. Okay? Or the negative acknowledgement. You're saying that things are not. Yeah.
That's what you said, yeah, and the right thing.
Yes. But with Ethernet, if I'm saying that you detect an error, what happens? Just drop it. So Ethernet is a fast technology where it doesn't need to have a delay within the actual correction or detection. Just drop it. And you need to retransmit that. Any question about the Ethernet frame structure? Is it clear? Should be fine. What's not clear? You need to synchronize the structure of frame between sender and receiver. Yeah?
You said that something that's used to synchronize. Surely, by the time it's been synchronized, the speed has changed.
How long does you think you synchronize?
I don't know.
You are dealing with
But
microseconds.
Yeah, exactly. At least a small bit, though.
There is delay. We should have a delay. Remember the delay we call the processing delay? That's the time we actually process everything. That includes that part of access synchronization.
But you said it was a difference if it's not synchronized.
Then the delay will be much higher. Put it that way.
Okay.
So there is delay, but how much delay? Look, we're not living in an ideal where there's no delay at all. But how long that delay can be reduced? How much can it be reduced? Provided that synchronization, ideally you don't want it. If those devices are clocked perfectly, then eventually you don't want it, but it's not.
I was thinking maybe it would cause errors instead.
And no,
If it's
having
just-
it will reduce number of
if it's
errors.
just speed, then-
Having it will reduce more number of errors rather than increasing it. That's, again, it's not me saying it, it's being tested by whoever is testing it, like IEEE, whoever creates it. Any questions? Ethernet MAC addresses. What are these? Again, MAC addresses.
Sorry.
MAC addresses are administrated by IEEE. So what does that mean? IEEE, they're actually giving you those addresses. They sell you some sort of addresses to whereas people to use, either companies or individuals. So what is MAC addresses? They are manufactured buyers to opt portion of the actual MAC address space to assure uniqueness. By the way, MAC addresses, when they first were created, never ever couldn't be breakable to be changed. So in other words, I couldn't change my MAC address. Although now, when I say before they actually created that book, that version, the fifth one I'm taking information from, is being broken, and now people can manage now to break the actual physical and change it without changing the actual device. So what I'm going to explain later on doesn't make any sense, but let's go with it. What happened? They tried the actual. Now they created software to cheat the system. They cheat the operating system to tell them I have a different MAC address. People say, "How will you do that?" I'm not a hacker. I don't know how to do it. But people have already been doing it by changing the actual physical address. So when they first created it, they just said, no one can change it because it's a physical part. No one can change a physical part, but they can now. Put it that way. Yeah, people are just, yeah. MAC addresses are like a P number for you. So in other words, what does that mean? It means that you're not stuck in one place. I can't take that line and put it in a different PC. You'll still inherit that physical number. You as a student will have a module. You can't go to a different module. But still you have your own ID. Nothing will change. It's not like a flat address where you cannot take that flat address anywhere because it's stuck with that place. If that makes sense. So an actual addresses that will be associated to the LAN itself, to the NIC, to the network interface card. Okay? That's why it shouldn't be broken in a sense. To create that sort of flexibility in a sense. But now, you don't deal with it. How does it look like? For Ethernet network interface card, MAC addresses is a 48 bits, which called the physical addresses. Typically coded in hexadecimal. An example, that's your MAC address. If you open your mobile device at the moment, go to settings, and go to the actual networking where you have an actual physical address, you'll see something similar to that, but with a different number. Those bits, those hexadecimal parts, should have a meaning, okay? And I'll explain to you what are these. The first two bits are an I and a U. An I indicates a broadcasting or a multiclassing addressing. So if I have 1 inside of an I, that means it's a multiclass or broadcast. What does a broadcast mean? Let's explain last lecture.
Broadcasting to multiple.
So you send to everywhere, broadcast it to all the information, like a TV broadcast. So that's your broadcasting, or a multicast. You send it to multiple users. A unicast, if it's a 0, it's a unicast. It's a 1 user to a 1 user only. That's it. U means it's either a universal or an actual local. We just mentioned that LAN was first created towards a LAN technology, not for a wide area network. But eventually this started to be evolved towards a wide area network. Therefore, we needed to have an indication of a universal address rather than just a local one. And that second bit will play that part. If it's a 0, it's a universal one. Meanwhile, if it's a 1, then it's a locally administrated. The other parts, now we have the other parts of the actual structure. The first 2 parts are assigned by IEEE. So they sell you that part. And the other 3 parts of the actual physical address is you to associate to different users. Similar to the actual IP addresses, where you have 1.8, 186, 192, 168, 01. Then you have 2, 3, 4, 5, 6, 7 towards the end of the domain, or the subnets. These are being associated by the admin, but you've been sold the first part, and you distributed the next part. Same with the MAC addresses. You've been distributed the first part, you bought that part, and you distribute that to your users. You start creating those new physical addresses. So IEEE sold those to 3Com, sold them to IBM, and asked them to create those NIC cards, okay, to be produced to other people. An example of those, 3Com owns 006008 towards a specific range. Meanwhile, IEEE 802 committee owns 0080CS. And again, these are owned by people, and then they distribute the other parts of it by creating new physical parts. Again, these are hexadecimals. So we're dealing with around 17 million physical addresses. Count that up. If you want to see all the standard numbers being associated, who bought them, that's the link you want to go to. Standards, I don't think anyone would be interested. But if you are curious to see who bought everything and where it's exactly residing, and if you want to buy something, that's there to buy it. To create your own physical address, put it wherever you want, just to hold it on. Yeah?
Can 2 suppliers create the same address?
No, you never should have the same address.
How does
If
it?
that being created, then you'll have that portable conflict of an actual physical device. That's the part where when people started to play with the software, they tried to create that duplicate numbers. So in the end, your device will end up not accepting any frames coming in and out of your device because there is an actual conflict of that physical address. That's a part of the hacking system where they wanted to create. Same as the IP address. If they are matching by any, if you create the auto assignment and you enter the house and for any reason one is using the same IP address, what the message you'll have? You cannot use the IP address because there is a conflict within the IP address. These are changeable, easy to change the numbers. But with Macs, you cannot change the numbers. Just throw it away. Any questions? Network administrator can use application software to add and maintain group addresses on a network interface card. Multicast addresses, that's what we call the multicast addresses. So you send to a number of users rather than broadcasting it to everyone in the line. If you have a MAC address that looks like this one, all ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it looks like ones, what does that mean?
That's a mask.
What's that?
Mask.
So what does it mean? That means broadcasting. if you have that address, you're sending that address as your destination, for example. There's no such address. That means this is being distributed to everywhere in the network. That's it. So there's no physical address at once for the 48 bits. They are just an indication to the system to broadcast it to everywhere in your network or in your segment, whatever that is. Okay? You'll need that because whenever I show you the plug and play part, you need to understand that part of it. One's an actual physical, because they are hexadecimal. One's is FF. So they should be an hexadecimal in this way. So these are your broadcasting addresses. This is example of your actual LAN or wired or wireless topology where you have a star configuration with 4 interfaces, adapters of 4 different devices. Very simple, straightforward. How will this look like in your actual configuration machine? If you go into your configuration part, I think if you know how to do configuration within your Windows or Mac or Linux system, you do ipconfig, you see the configuration within. This is, if you press that, you want to see the MAC addressing table, that's how it looks like. It has a virtual LAN address, the MAC address itself, the type of the address, and the port number is being connected to. Again, you don't need to bother yourself with those details. I just wanted to understand the concept of MAC addresses and how they look like and why they are important within your devices. We'll have a fast break at the moment because this slide finished. So I'll have 5-10 minutes break and I'll come back to finish.